Okay, hi. Okay, good afternoon, everyone. Welcome to the session from solid state drive, and I'm the session chair today, Yu Liang. And in today's session, we have three paper presentations. And the first one is titled Integrated Subpage-aware write method in large page-based SSD. And the presenter is Jin Shen Wu. Let us welcome the presenter.
Okay, so hello everyone and good afternoon. And my name is Jin Shen Wu, and I'm from National Taiwan University of Science and Technology. And today I will present a subpage-aware write method in large based SSD. The work is based on my master student Oh Yang thesis. Okay. So here is our outline. Okay, so we know solid-state drives adopt NAND flash memory, and SSD has been widely used in various systems, maybe laptop, enterprise storage. And in NAND flash memory, best unit, read-write unit is a page. We call page, and a page cannot be overwritten. Okay, unless its residing block is erased first. But the block is large than a page. Usually, a block maybe contain maybe 200 pages. And another features is our press update in flash memory. So it means if when you want to write update data, you have to write the update data to a new page, and then the corresponding old page will become invalid. Okay, so later we will trigger garbage collection to recycle the valid page. And based on the current manufacturer processor, page size usually maybe 512 byte, but now it's increased to maybe 16 KB in recent years. But for file system, its I/O request is based on a sector, and a sector size is maybe 4 KB. Okay, so when you access a 16 KB logical page, yeah, maybe even you access a 4 KB sector, but you have to really access the physical page, and its size is 16 KB. Okay. So because the difference between the 16 KB page and 4 KB sector, there will be a subpage write problem. Okay, in the flash memory. Okay, and although SSD have internal buffer to temporarily store the update data, but the problem, okay, a subpage write problem, okay, still exists when the buffer is full. Because when the buffer is full, you have to write the content of the buffer to flash memory. And the previous study have been proposed to handle the subpage write problem. And we also observed two different methods to handle the subpage write. So in the paper, we want to utilize the two different methods, and we propose a subpage-aware write method. Okay, and our objective is to reduce the overhead of subpage write. And here is our background, okay, background knowledge. Okay. So here is okay. Oh, okay. Okay, here is the base structure of SSD. So we can see in SSD we have a DRAM. Okay, in DRAM we have a buffer, and the buffer can temporarily store the data. And we have a mapping table. Okay, and the mapping table is to record the mapping from a logical address to a physical address because of our press update. Okay, and so inside SSD, we have a FTL module, okay, flag translation layer, and FTL, its purpose is to maintain the buffer. So we have a buffer management, okay, and he also handle address mapping. So he FTL must handle mapping table. And just what I mentioned, because you have to recycle the embedded page, so FTL have to trigger the garbage collection to recycle the embedded page. Okay. So here is the best structure of SSD. Okay, so we can see we have a DRAM, we have a buffer and mapping table. So in the paper, we will focus on buffer and mapping table to handle the subpage write problem. So here I will introduce logical sector number and logical page number. Here I say a logical sector number is small, but logical page number is large, because I just say a sector maybe is 4 KB, but a page is 60 KB. Okay, so logical sector number we will call LSM. Okay, maybe it's in use in a file system. Okay, so here we have a write request. Okay, and LSM mean the starting LSM. Okay, and size is the number of sector that the write request will write. Okay, so in this figure we can see, okay, a small write request or a large write request could cause the problem of subpage write. Okay, this is the normal case. Okay, if we have a write request W04, okay, because its starting offset is from 0. Okay, so the fourth sector can be fully written to a complete logical page like this. But W41 is just write only one sector. But even you only write one sector, you have to write a fully page. Okay, because I say a read-write unit in flash memory is a page. Okay, here the write request W94, even it also write 4 sectors, but based on the offset, it had to access 2 different logical page number. So W94, the write request, you see, it just write 4 sector, but when you translate the address mapping, the write request have to write to different logical page number. So it also means you have to write to different page. Okay. So this is what I say, subpage write problem. Okay, and so in the paper we want to to reduce the subpage write overhead, okay, as much as possible. Okay, so this is our motivation. Okay, so okay, when the buffer is full, we know some 30 LPN will be selected, will be evicted, and returned to flash memory. Okay, and here we assume, okay, LPN 0 had been returned to PPN5. Here, PPN5 means a physical page number, okay, with 4 sectors, okay, and LPN1 had been returned to PPN6 with only 3 sectors, okay, because some logical page some logical page are fully written, but some logical page may be partial written. Okay, so here, okay, PPN5 is fully written and PPN6 is partial written. Okay, and now we assume in the buffer we we have 30 sector in LPN0, okay, and we have 330 sector in the LPN1, okay, in the buffer, okay. So you can see this is the new data and this is the old data, okay. So in the previous study in UFS, okay, you will when for example when LPN0 will be returned to flash memory, it will correct other related sector, if any, okay, to form a free return LPN. For example, if you want to write LPN0 from the buffer to flash memory, so UFS have to correct other related sector 1, 2, 3. Okay, so he will read from PPM5 and okay to form a free written LPN, and then he will write to another new page, maybe PPM7. Okay, and then it will become invalid. Okay, so LPN1 similarly. Okay, LPN1 will be returned to maybe PPN8. Okay, and PPN6 will become invalid. Okay, so in UFS, you can see that its write method is try to okay correct the redacted status. Okay, so it will bring some overhead. For example, even you only write one sector, but you have to read another related sector, right? Okay, so this is overhead. Okay, and in another write method we call SLC. Okay, it will be different. Okay, it will mix the related sector of LPN0 and LPN1. For example, when this sector will be returned from buffer, okay, SLC will merge these sectors in the same PPN as much as possible. So in this case, you can see these sectors will be returned to maybe a PPN7, okay, and we call a mixed LPN01, okay. So we have two different write methods, okay, you can see. And in the paper, we want to, and this method has layer advantage and also they have layer disadvantage. And we want to utilize layer advantage, okay. Okay, so just what I say, the first method is UFS. The first method can bring extra page read because he have to correct the related sectors, okay. And the second, and also he will extra page write because when you correct the sector, you have to write more sectors, so he will cause extra page write. Okay, and the second method can bring another extra page read. I say another for the read data, because when you mix different sector of different LPN in the same PPN, it also means when you want to read LPN, this sector maybe could be scattered or stored in different PPN. So maybe you want to read LPN, but his sector are scattered, are stored in different physical page. You have to read more page. Okay, so I say another extra page read. Okay. So in the paper, we want to propose, I say, a subpage-aware write method to utilize the advantage. Okay. Okay. So I think it's clear. Okay. This is our object. Okay. And our idea is it's okay. It's not complicated. Okay. Here is our architecture. So we have a subpage-aware the waiting buffer management. Okay, so when the buffer is full, yeah, we have to choose some LPN and then write to flash memory. And we have some condition. Okay, we will detect if they are hard read or cold read. If they are hard read, we will use compact LPN. If they are cold read, we will use non-compact LPN. Okay, so based on hard read, cold read, compact LPN, non-compact LPN, we have a 4 type. Okay, 4 type LPN, just like this. And then we will use mixed PPN. The mixed PPN will mix hard write data in the same PPN. Okay, and cold write data in the same PPN. Okay, I think if you know hard code data identification, yeah, we will try to put the hard data in the same PPN or in the same block. Okay. Okay, so this is our system architecture. Okay. Okay, so here we will have a buffer. So in the buffer, we know because each LPN could contain a fixed number of sectors. So in the buffer, we have maybe a fully used LPN. A fully used LPN means it will store all related sectors. For example, LP10 is a fully used LPN. Okay, so another we will call partial used LPN. Okay, maybe we'll store some related sector. So LPN4, LPN10, and LPN6 are partial use LPN. Okay, so in this sector we have also 3 types. Okay, maybe in the buffer maybe we have a dirty sector. Dirty sector means the sector has been modified. Okay, and clean sector means the sector is read but not modified. And we have empty sector. Empty sector means it's a free sector because it's partial use LPN. So it will have some empty sector. Okay. So in the paper we define a weighting for each LPN. So this is the some parameters. Okay, this is the weighting, and based on the weighting, we will choose the LPN with the minimal weight to brush out this LPN. Because if LPN with minimal weight, if LPN with the minimal weight, it also means the LPN is distantly used. Okay. So we will try to select this LPN with minimal weight, and then we will maybe compact or non-compact this LPN, and we will use mixed PPN to write this LPN, just what I said. Okay, so here is example. We will assume in the paper we show an example. If we have 2 different LPN, maybe LPN0 and LPN1, and based on the parameter, we can calculate their weight. So for example, LPN0, his weight is the number, and LP1 is the number. So based on our weighting eviction, we will choose LPN0 to write out. Okay. So in fact, the compact LPN is based on UFS. So you can say UFS always use compact LPN to write the data from buffer. And in SLC, he will use non-compact LPN to write the data from buffer. So here, what is compact LPN? Compact LPN I just mentioned, yeah. When you want to write, maybe is the part of here LPN0 is the partial use LPN. When you will be written to flash memory, you have to collect other related sector, and then you write to another free page. So we will call compact LPN mean you have to collect other sectors. So we call compact LPN. But what is non-compact LPN? Non-compact LPN means, okay, if you want to write the 2 partial use LPN, they will be merged. Okay, they will be merged in the same. They will be written. They will be merged and then written to a full page as much as possible. So we can see compiler PN will make extra page read, right? You can see from the example, okay, and some extra page write. But the advantage is compiler PN can decrease the number of page read if the compiler PN is accessed often in the future, because their data are stored in the whole physical page. They are not scattered, they are not stored in different multiple PPN, okay? So now compiler PN, they are accurate, okay? So now compiler PN, okay? Yeah, because you have to mix different sector in the same PPN. So now compiler PN will bring another page read, okay, for the read hard data, okay? Read hard data means the data is read often. We call read hard data. Because non-compiler PN may be the whole LPN may be stored in different PPN, okay, based on non-compiler PN. So when you read the LPN often, you have to read maybe 2 or more physical page. Okay, so I say another extra page read. But the advantage is you can save the storage space, okay, and avoid extra page read and write during the buffer eviction. Okay, so we have 2 different write methods, and they have their advantage and disadvantage. So we want to base on the data characteristics, data features to utilize their advantage. Okay. Okay, so in the paper, we will choose mixed LPN. Okay, we will not choose. Here's not okay. It's a title. Here should be mixed PPN. Okay, this is a title. He should mix PPN and not mix PPN. So in the paper, we use the mixed PPN. The mixed PPN is like this. If they are returned to flash memory, we will try to mix their sectors in the same PPN as much as possible, because we want to save, we want to reduce the page write. Okay. Okay. So in this case, non-mixed PPN will cause 2 page write, but a mixed PPN just 1 page write. Okay. So the concept of the paper, okay, is based on their advantage. If the data is hard data, we will choose compiler PN, okay, based on the advantage of compiler PN. If it's a core data, we will use non-compiler PN, okay. And so based on hard core and compiler PN and compiler PN, we have 4 types of PN, okay, and then we will mix hard data in the same PPN, okay. It means if this sector are hard sector, maybe they belong to different LPN, but if we have a free sectors, we will try to put in the same PPN as much as possible if they are hard data. Okay, and core data we will mix in the same PPN. Okay, as much as possible. Okay, so here is our performance evaluation. So in here, we measure the number of page write, the number of page read, the number of block address, and the size of mapping table. And here is some related parameters. Okay. So we use the real workloads like this from the association. Okay. So here are the characteristics, these worst features. Okay. So so on average, you can see my mean our proposed method, okay, and UFS and SLC are 2 different write methods. So on average, yeah, we can reduce more page write than other methods. Okay. Okay. So Similarly, our performance also can reduce more page rate than another method. Okay, and block erase similar, yeah, because we can reduce page write, so we can also reduce the block erase. Okay, and okay, so here, UFS will use the small mapping table because it always use compact LPN. So his LPN, his status of the same LPN will not scatter to different PPN. So his mapping table will be the small. Okay, but our method will be between UFS and SLC. Okay. So this is our conclusion. So in the paper we introduced the subpage-aware problem, and we also introduced two different writing methods, their advantage, and then our method is to utilize their advantage, okay, to improve the system performance. Okay, and thank you. Okay.
Thank you for your excellent talk. It's very clear. Does anyone on site has any question? No? Okay, I have one question for you. You have mentioned that in your work you classify the data LBN to 4 types, right?
Yeah. Yes.
So I want to, I would like to know if this LBN may change their types during the garbage collection process or during maybe IO time.
Yeah.
If this LPN,
LPN.
yeah, LPN change their type.
Oh, okay.
During the maybe garbage collection process or
okay.
IO time.
Yeah. It's like maybe agent problem. Yeah, if they change, yeah, maybe they will change their type. Maybe his hard data, and sometimes it change to correct data.
Yes.
Okay, so yeah, here our method just focus on the data are written from buffer. So
just from the buffer to fresh.
Yeah. So in the paper, we do not consider the case just how you mentioned.
Okay. So
maybe
you can optimize.
Yeah, maybe in the future we can consider your case. Okay.
Okay. Thank you.
Thank you.
Okay. If there's no question, we can move to the next presentation. Let us give the presenter the big hand. Thank you. Okay, the next paper titled Nimble Mapping SSD that mapping strategy to increase reliability of 3D TLC charge trap NAND flash memory. And the speaker of this paper is Wenlin Xu. Let us welcome her to present this paper.
Hi everyone, my name is Wenlin Xu. Today I will report the paper in place of the author. The author of the paper is Zhijia Chen and the Professor Xie Renwei. The topic of my report today is Nimble Mapping SSD, learning state mapping strategy to increase reliability of 3D TLC charge trap NAND flash memory. This is the outline of the paper that I'm going to report. We get started with the introduction and background, then introduce the Nimble Mapping SSD, and last is the experiment and conclusion. First, let's get started with the introduction. As manufacturing process technology node continue to shrink down, traditional NAND flash memory faces scaling limitation because of data reliability issues. 3D NAND flash, which adopts the charge trap cell design, is suitable for high-end SSD market due to the reduction of cell-to-cell interference and excellent endurance characteristics. In planar NAND flash, peer work has shown that retention error and write disturbance are the major sources of the bit errors. NAND flash to reduce write disturbance and retention error. To migrate error, we adopt the bit flip technique in our design, which will be described later. According to the characteristic of data, we developed the strategy to write data in MSB, CSB, or LSB page. We divide the written data into chunks, which is the basic unit to be flipped, and identify the data pattern of every chunk. Then let's introduce the background of TLC NAND flash memory. First, let's see the structure of the NAND flash memory. The figure of the left shows the structure of a charge trap cell. The charge trap device is an insulator that holds charge of the transistor. On top of the cell is control gate, and below is charge trap. Both sides of the charge trap are oxide layer. The upper one is control oxide, which is also called blocking oxide, and the bottom is the tunnel oxide. The tunnel oxide and blocking oxide isolate the charge trap to prevent charge from leaking out of the cell. NAND flash memory has three basic operations: program, which also called write, read, and erase. Program and read operations are performed in the unit of a page, while erase operation is performed in the unit of a block. Figure of the right describes the physical organization of 3D NAND flash memory chip. A 3D NAND flash memory chip consists of thousands of blocks. All the control gates in the same layer form a wall line. By adopting charge trap cell in NAND flash structure, the cell-to-cell interference has been reduced. 3D NAND flash memory become a mainstream in storage markets. This paper focuses on TLC NAND flash memory for research. Each flash cell stores 3 bits of data, which are referred to as the most significant bits, MSB, the center significant bits, CSB, and the least significant bits, LSB. In order to represent all values, the range of threshold voltage is divided into 8 states in TLC NAND flash, which we could see at the figure is S1 to S8. All the cells must be at the erase state, which is S1, before data programmed to the cell. Due to the process variation, the threshold voltage of cells programmed to the same state is normally distributed. In TLC NAND flash memory, the 3 bits of each cell in the same wall line comprise 3 pages, which are the unit of written data. Figure presents the organization of a flash block. Each block is comprised of 96 wall lines. All the cells in the same wall line are read and programmed together at the same time. All MSB bits in a wall line form a MSB page. All CSB bits in a wall line form its CSB page, and all LSB bits in a wall line form a LSB page. The programming method commonly used in 3D NAND flash memory is full sequence programming, as the interference issue is not severe. Next, We are going to introduce two major sources of bit errors. Retention error results from the charge leakage, which causes the threshold voltage shift from a higher state to lower states. The retention error becomes more and more serious as PE cycle increases. Higher state causes more shifting and incurs more serious retention errors. Program variation error is the random variation presented in the program operation. When cells are programmed to higher states, their threshold voltage are actually distributed across the voltage window. As NAND flash memory experiences more PE cycles, the program variation would widen the threshold voltage distribution and cause bit errors. However, 3D NAND flash memory has different error characteristics because of the evaluation of cell structure and material and mental gate material. In this paper, we focused on 3D charge trap NAND flash memory and deal with two major sources of errors. The first one is retention error, and the second one is program errors. Then we introduced the Nimble mapping SSD, which we call NMS, which is the main method of the paper. Figures show the system architecture of the proposed Nimble mapping SSD. The goal of design is to increase the number of specific states to avoid the worst case data. And priced by WBVM, we decide the written data into several chunks, which is the basic unit for flipping. In WBVM, paper calculated error sources to determine the flip operation every wall line. However, calculating the error sources can be time-consuming. In addition, since the unit of calculation is a wall line, WBVM has to catch the written data. The request handler processes the page alignment of every request and decide the physical location where the data would be returned. We designed the pattern identifier to find out the data chunk that need to be flipped. The pattern identifier counts the ratio of 1 in every chunk. Then the scrambler processes every chunk to increase the ratio of 1 or 0. Let's introduce the right strategy of Nimble mapping SSD. The sensitivity to threshold voltage shifting varies from state to state. As period work shows that write hardness can affect data integrity. We also take the write behavior into consideration. For the hard data, the time between two write requests is short enough to prevent charge leakage. Thus, the main error of hard data is program disturbance caused by the program variation. For the cold data, the retention time is long and the retention error dominates the error of NAND flash memory. Period work shows that the first one, the higher states suffer more serious left shifting, and the second one, the lower states are sensitive to right shifting. That is, error induced by the program variation occurs at the highest probability when the cell is programmed at S1. Retention error occurs at the highest probability when the cell is programmed at S8. Figure of the left shows the conventional mapping way used in the TLC NAND flash memory. MSB designed the cell to be programmed to the lower state or the highest states. When the cell MSB is 1, the threshold voltage state of programmed cell will be limited to S1 to S4. By controlling the MSB, we can program the cell to higher or the lower state. So when MSB is 1, we could program at S1 to S4. When MSB is 0, we could program the cell at S5 to S8. So no matter what state a cell is, bit error may happen in the LSB page due to the schedule voltage shift. So for example, when the cell is shifted from S1 to S2, the LSB bit will be the error. The range which can determine the state of a cell called domain region. If the data is right hot, the program variation dominates the cause of the error, and thus higher states are more appropriate. For the code data, lower states are suitable due to the retention errors. In a conventional mapping, when the CSB is 1, higher state, which is S5 to S8, will be concentrated in the S7 and S8, while the lower state, S1 to S4, would be programmed at S1 to S2. CSB domain region cannot distribute the schedule voltage state to the higher state or the lower state. In our design, which is shown in the right, the conventional CSB domain region is divided into CSB and LSB, which is shown in the right here. In the CSB domain region, we can increase the probability that the state being set at S1 and S2. For the LSB page, increasing the ratio of 1 can increase the probability that the cell being set at S7 and S8. To manipulate the schedule voltage state of a fine grain, we redesigned the mapping, which also coincides with breakcode. That is, in the TLC NAND flash memory, the 3-bit value of the adjacent threshold voltage state different only in 1 bit. So we could see at the figure that S1 and S2 only different in LSB bits, and the S2 and S3 state only different in the CSB bits. Table shows the strategy to process every chunk. For code data, the MSB and CSB dominant region are used to increase the number of lower states. Thus, the MSB and CSB page prefer to be 1. In the LSB domain region, increasing the ratio of 0 can place more cell at S5 to S6 when the CSB of the cell is 0. High state is suitable for hot data to prevent program variation. The MSB bits prefer to be 0, and the LSB bits prefer to be 1 to increase the number of high states. In addition, the CSB domain region is used to place more cells at S3 or S4 when the MSB is 1. Then we are going to introduce the step of Nimble mapping. To antisymmetrically encode the written data, we designed the pattern identifier and the scramble to process every chunk. Figure illustrates the data flow of the pattern identifier. The data is first divided to several chunks according to the data size and the chunk size. The counting circuit in the pattern identifier then counts the number of 1. If the ratio of 1 is more than half, the R bit is set to 1. Otherwise, the R bit is set to 0. Once the pattern of written data is identified, the R bit is sent to the scrambler, which I am saying you could see at the figure that the data we input would divide it into several chunks, from chunk 1 to chunk -1. The chunk size is based on the data size and the chunk. So the counting circuit will count every chunk, the ratio of the 1 in every chunk, and output the R bits. So if the ratio of 1 is more than half, the R bits will be 1, for example, in a chunk 1. We modify the scrambler and summarize in algorithm 1. To determine the F-bit action of a chunk, the content of chunk is obtained from the pattern identifier and sent to the R array, which you could see at the top in line 1. We introduce the F-bit to indicate the flip operation of each chunk. Different combination of the preferred bits and the R bit is shown in the table. The preferred bit was set based on the table that we introduced on page 13, which is based on the page type and whether it is hot data or cold data. By checking the preferred bits, we can generate F-bit from R bits. If the preferred bit is 1, F-bits are generated from the flipped R bits, which you could see at line 3. In the opposite, F-bits are equal to R bits when the preferred bit is 0. You could see at line 5. In summary, if the chunk needs to be flipped, the F-bit is set to 1. If the chunk will remain the same content, the F-bit will be set to 0. The written data is then segmented to several chunks by the chunk size, which you could see is line 9. For each chunk, the scrambler value verifies whether the chunk should be flipped by the inverter based on the F-bit, which you could see is line 10 to line 12. The chunk data would remain the same when the F-bit is set to 0. The F-bits along with the data are written to the NAND flash memory, which you could see is line 14. Because the F-bits are stored in the spare area, a trade-off between chunk size and encoding efficiency is considered. The last is the experiment setup and the experiment results. We implemented a simulator to evaluate the reliability of proposed NMS design. The experiment parameters are summarized in Table 3, which is shown in the left. The simulator adopted greedy algorithm to select the victim block when conducting a garbage collection. Table of the right lists the characteristic of the workload. According to the request size, we simulated the written data by randomly generated bit sequence. We selected 6 workloads from MSR Cambridge workload. We compared the following method with the selected workload in our experiment. The first one is baseline, which is the written data without encoding. The second one is WBVM, word line batch VTH modulation strategy. Determine the flip operation every word line. And the third one is NMS, our proposed Nimble mapping SSD mechanism. To evaluate the reliability of NMS, we analyzed error of baseline, WVBM, and NMS in terms of retention error and program error until 3,000 PE cycles. The experimental result was normalized to the baseline after the PE cycle reaches 230. Figure shows the retention error under each workload. Compared with WBVM, our proposed NMS could reduce retention error by 1.2% on average. In most cases, the retention error of NMS was lower than WBVM. In Web 0, in Web 0, which is shown in the right here, the retention error of NMS was 1.4% greater than WBVM. We surmise that was because some code data might be misidentified as hot data. In addition, WBVM encoded hot data to lower states. Therefore, the misidentification of hot data slightly affected the retention error of NMS. Figure presents the program error under each workload. The proposed NMS averagely reduced error by 17.1 compared with WBVM. In WBVM, hot data suffered more program error with 13.5% higher program error than the baseline on average. NMS strategy took the characteristic of 3D charge trap NAND flash to consideration and program hot data to higher states. Compared with WBVM, NMS even reduced the program error up to 20% in the SRC2-0 workload because the data was updated frequently and the transfer size was small. Our proposed NMS strategy efficiently programmed the hot data with high state cell. In worst case, since the code data occupy most of the write request, NMS just reached error by 0.08% compared with the baseline in WDEV-0 workload, which you could see in the middle. The last is the conclusion. This paper we propose Nimble mapping SSD NMS to anti-symmetrically encode the written data based on the access behavior of the bit pattern. The goal of our design is to reduce the bit error incurred by write disturbance and retention error. NMS could anti-symmetrically encode the written data to higher or lower schedule voltage states based on the update frequency of written data. Compared with WBVM, we could improve the reliability of NAND flash. The experiment results shows that our mechanism could reduce 1.2% retention error and 17.1% program error on average. Thanks for your listening.
Thanks for your great presentation. Does anyone here has any question for the presenter? Okay. You have a question.
To shortly conclude the advantage of NMS compared with WBVM.
Actually, the paper is implied by the WBVM. You could say that the paper is changed the method of the WBVM. The main idea of WBVM is that they decoded the written data into several chunks, which is the basic unit. Compared with WBVM, we divided the written data into several chunks, which is the basic unit for flipping. But in WBVM, the author calculates the error score to determine the flip operation every wall line. So the main disadvantage of the WBVM is that they calculated the bit error to be flipped every wall line. So WBVM have to catch the wall line data. It is time consuming. So the paper that we change is the main key point here.
Any other questions? another question for you. The main concept of your research is to feed the data based on the data characteristics. I'm wondering to know if it would have a negative impact on scrambler.
For all of our knowledge that the written data right in the NAND flash memory is most important, that we need to be randomized. So in this paper, you could see think that the scrambler is being disabled, or the scrambler could fit the idea that we bring up. So there is no worry if that the written data that we write into the NAND flash memory is not randomized enough.
See, thank you very much. If there are no questions, okay, thank you for your presentation. Let's move to the third paper. The third paper is presented by Hassan or Hassan. Let's welcome him for his presentation.
Okay, so hi everyone, my name is Hassan. Today I'll present the technique RUSM on behalf of the other co-authors of this work. The basic problem we are tackling in this research is the read-write interference problem. Basically, in the NAND flash chips in the storage system, when there is a command that's ongoing on the NAND flash and there is another command wishes to start on the same chip, the later command should wait until the first one finishes, which adds to its latency. The read requests are harmed in terms of latency more than the write request, because the write requests take longer time to execute. So the read request will wait ongoing write request for a very long time. For the sake of quality of service in the storage system, consistent and predictable latency is always demanded all the times. This problem becomes worse in the 3D NAND new technology because of the large page size. The larger the page size, the longer the time a command needs to finish execution. So a vital solution we're thinking of in this research is to replicate frequently accessed data. The idea is straightforward as simple by just copying the frequently read data into different chips. So if one of the data is blocked by ongoing write requests, another copy is available. However, this technique has a term of because of the high overhead. In order to do the replication, we need to read the data out of the NAND flash and then write it again into a different chip. That will add more internal read and write workload, and that will reinforce the original read and write interference problem. So the insight we are looking for here, we need to find some wasted time resource inside the storage system. In particular, we are looking for some redundant write that's done by the flash controller internally and was not asked by the host. If we can find that redundant write and replace it with the replicated data write following the flash writing policy, then we actually can hide the replicated data overhead, because we just replace write with another write without adding more write amplification. Shortly, I will show to you what I mean. So let's take a look on how the SSD writes the data. We have two basic cases. The first case is if the data request coming from the host is of a page size. In this case, the process is straightforward. A flash controller needs to invalidate the original page and write the requested data into the new free page. On the case 2, the situation is different. The data is smaller than a page size. We call this subpage write. In this case, the flash controller needs first to read the valid data out of the page, merge it with the new incoming data request, and then invalidate the page, find the free page, and write the merged data into the free page. If you can mind here that redundant write happened in step number 1 for the case 2, that repeated data, this data write was not asked by the host. It is just done by the flash controller because of a flash write policy. Now we start to think about, can we replace that read modify write, we call it read modify write, with a replicated data write? If we can do so, then we can actually hide the overhead of the write request that we use to replicate the data. And here's how RUSM works. This is the general overview of the scheme. When the data is being read from the NAND flash, they are buffered inside the read cache. This is just straightforward from the conventional scheme. However, we try to identify the hot data right in the read cache. And when there is a subpage write, a write which is smaller than the page size, coming in the write buffer from the host, we take it, we collect some hot data from the read cache, and we do the merge, and we do the replication. If we didn't do this process, we simply do the read modify write for the incoming subpage write coming from the host. So we pay the cost one time instead of paying the cost twice. We avoid the extra read here because we just take the data from the read cache. We use the same original read data command, and we avoid to conduct extra write, as I said, because we replace the read modify write. So the idea is just straightforward and simple. We just try to use some redundant wasted resource. Now I'll start talking about the design of the scheme. First, we talk about the read cache design. As I said, we need to identify the hot and cold data of the system, and we need to do it inside the read cache. Because we are dealing with 3D NAND technology as a target system, we are expecting a huge number of data. So we will try to avoid tracking every piece of data, the frequency of access of every piece of data by storing counters, for example, as a metadata. We need to do it seamlessly and natively. To do so, we decided to use 2 different data structures in the read cache. Linked list in particular, one for the cold data and one for the hot data. When the data is being read from the NAND flash, it enters the tail of the cold list. And whenever there is a read hit in the read cache, it's moved logically to the tail of the hot list. I say moved logically because we actually change the pointers and we don't move the data physically around. So the tail of the hot list is the most frequently used hot data. And the front of the hot list is the least frequently used hot data. When the space of the read cache reaches some limit, we take the data from the front of the hot list, which is the least frequently used hot data, and subject it for replication with RUSM merge technique that I'll describe later. So we keep the more recently used hot data into the read cache with higher priority, and we replicate the least recently used hot data that's still usable. Let's call it warm data, and replicate it on the NAND flash, creating a tier 2 of read cache extension in the NAND flash. Now I will talk about the merging and mapping, but before I do so, I would like to give you a background of how the conventional scheme maps the data. In particular, I will talk about the page level mapping. From the host, the SSD is viewed as a set of logical contiguous sectors. Each sector is 512 bytes. The request comes from the host in form of logical sector address, followed by the size of the request. So the contiguous following logical sectors is known implicitly starting from the logical sector number. Then the FTL will generate one or more logical page numbers, and then map those logical page numbers into physical page number to write the data actually on the NAND flash. Something very important to notice here is that the FTL will write each logical sector down into the NAND flash at a specified fixed offset on any selected page. For example, in this case, depending of course on the size of the page, logical sector 0 is always written at the offset 0 of any selected page. Logical sector 4 is also written at offset 0 of any selected page. This is very important because that's what gives the page level mapping its simplicity. We don't need sector level mapping because sector offset are known already. We just store one-to-one, one entry per address inside the mapping table. And we need to follow that principle also with our scheme. So we don't vary so much from the mapping, conventional mapping, page level mapping. Now we talk about how we merge and map the data with RUSM. Actually, the situation is different because now we are mixing heterogeneous data inside one page. So in order to do that sufficiently, we need to merge subs, one from the write buffer, which is come from the host, and one from the read cache, which is the hot data, avoiding mixing those subs that have conflict offsets that calculated by the conventional scheme. And we need to do that because we also need to avoid the sector level mapping. Otherwise, the overhead will be too huge. The cases of the subs positions are three. The sub either can start at the beginning and somewhere in the middle, or start and end in the middle, or start and middle and fill the rest of the page. So now with this just small technique, we can reduce the need of sector level mapping into sub-page level mapping instead, which is a variation from the conventional page level mapping, and we store the mapping for the replicas into a secondary table. So the SSD now have two tables, one primary table to store the normal data, and one secondary mapping table to store the addresses of the replicas. Now we have another problem. We cannot allow the secondary table to grow on the free space. We need to control the overhead, space overhead taken by that table. In order to do so, we set an upper bound to the aggregate number of the entries on both the primary and secondary table. And that upper bound is accepted by the conventional mapping scheme. So if that upper bound is hit at any time, we need to free slots from the secondary table, favoring the space to the primary table. And we cannot do that just randomly. We need to mind the least recently used and most recently used semantics and delete the data, the really outdated hot data. To do so, we use a data structure linked list that stores the replica LPNs forming a chain from the least recently used replica LPN to the most recently used replica LPN. So each replica LPN points forward to the LPN that's accessed after and points back to the LPN that accessed before. And here we go back again to the upper bound. When it's hit, we simply delete the data pointed by the least recently used. That's a fair idea how to delete the outdated data. Now talk about the evaluation. From the read latency perspective, in addition to the baseline, we compare RUSM to other three replication techniques. Two of them are heuristic, and one of them we take it as a comparable approach to our paper. The first one is replicate cache reads. We simply replicate all the reads previously cached in the system and ejected from the read cache because there is no space. Second one is mirroring. We simply replicate all the written data to the SSD. And the last one is hot read data replication, which is an on-demand data replication that tracks all the data in the system, decide which one is hot, and on-demand copy that into a staged area. We can see that RUSM outperform all the schemes for different percentile of read requests. And the reason for that is RUSM conducts less number of write requests because we just use the conventional read modify write time, replace it. Then that keeps less number of chips in the system busy all the time. That means more data availability, and that means more better reading performance. And that's what makes the RUSM different from other schemes. Now we talk about the write overhead in terms of write amplification factor. Again, RUSM outperform the other comparable approaches because it's again write less to the storage system for the same reason I mentioned. However, it still performs worse than the baseline because, as I said before, we remove the outdated data. And that process generate or left more invalid pages, more invalid data, and more data fragmentation than the baseline. And that means more garbage collection calls. And that's why the RUSM perform worse than the baseline that has no data copy at all. We try to solve that in the future by focusing more on the data locality. That's it. Thank you.
Thank you for your presentation. And does anyone here have a question?
Okay, very interesting work. And one question is about do you evaluate how the impact of the page size? Because we know that there are different page sizes based memory. If the page size is larger or smaller, what will be the impact? Yes.
The larger page size gives more chance for RUSM to work because that would mean we have more RMW, read, modify, write operations. And we actually evaluate that, but we don't show it here on this slide. So the larger the page size, the better for the RUSM to work on, because it's designed to work on large and write and work along with the trend of increasing the large page size.
Yeah. Anyone have questions? Yes. So I have one more question for you. In your experimental result, the result will the write amplification factor will be better when the overprovision ratio increase. So in your concept, do you suggest the SSD company to add more overprovision in the future product?
More over provisioning will be better for all replication schemes because that means that means less competition with the garbage collection. The garbage collection will be called less frequent. But it doesn't actually relate directly to the RUSM technique because RUSM technique can work on simply any over provisioning. However, if the over provisioning, increasing the over provisioning is better, for example, to do endurance.
So will the result better than just add another flash to when compared to add more over provision area?
Yes, of course. If we add more over provisioning area, then we will get better results with RUSM as well as other replication techniques.
Okay, thank you. Okay. So if there are no any other questions, I think we can finish this session. And I really appreciate all your participation here. So thank you for everyone.